Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. In the previous lecture, we took a look at this fairly common synthesizer structure. We have 4 low-pass filters, where each individual filter is a single-pole filter with a cutoff of a megaseed radians per second. And just having 4 of these in a series isn't terribly interesting. So we can add a negative feedback loop with a gain factor of k. And in the previous lecture, we saw how k could vary between 0 and 4, and at k equals 4, you would theoretically get self-oscillation. Now, how you implement these particular voltage-controlled filters is up to you. And in another lecture, we looked at a way that Bob Moog did this using a differential transistor ladder structure. Here we're going to be focusing on designs that use one-pole filters with OTA-Cs, operational transconductance amplifiers. One example of that is the low-pass filter in the Polyfusion modular system. If I recall correctly, Polyfusion was started by ex-Moog employees, and the Moog ladder filter was protected by patent, so they obviously couldn't do that. So instead they used 3080 OTA-Cs. The overall structure here is that we have a 741 playing the role of an input buffer, and then we have a series of these one-pole OTA-C filter stages. The current control pins of the OTAs are being driven by the current created by a voltage to current converter with an exponential characteristic. Now, we've looked at these before using NPN transistors to basically provide current sinks. Here they're using PNPs in order to provide a current source. So this basically works the same way as we saw previously in the lectures about oscillators, but here instead of a positive voltage, we have a negative voltage to create a reference current flowing through the resistor this direction. The rest of the setup is pretty much the same. We have this op-amp here that's designed to keep this collector node at a fixed potential. Here that potential is ground. The 15K resistor here is dealing with non-ideal op-amp effects. And the 100 picofarad cap here and this sort of local feedback loop is just for stability. The main logical feedback loop is happening all the way throughout here. And then we have some op-amps in front to combine different control voltages. So the versions of the circuit that we looked at that used NPN transistors needed a negative voltage here at the base relative to the base over here. And that was convenient because we usually needed to mix several control voltages anyway. So having an inverting mixer stage at the front sort of dealt with both of those issues at once. We could mix signals in a clean fashion, and we could also provide that negative voltage. Well, here with this PNP structure, we need a positive voltage here relative to the voltage at the base on the other side. So we actually wind up with 2 op-amps here. We have the first op-amp that's mixing a control voltage input with a control voltage that the user is just setting with a knob. That gives us a negative voltage here. And then we have another op-amp here that's inverting that again back to being a positive voltage. Notice that because voltage-controlled filters aren't terribly sensitive in terms of variations of the cutoff frequency as far as the human listener is concerned compared to a voltage oscillator, they're using a standard 1K resistor here and not using a temperature compensation resistor here or any place else in the circuit. So the output of the last filter stage goes to 2 places. It goes into this op-amp here that's buffering the output. The 100K resistor here is dealing with non-ideal op-amp effects. If you were using a better op-amp, you could probably just replace this with a wire. But the most interesting thing is the feedback loop where we set K, that feedback amount. Well, instead of just setting it with a knob, the Polyfusion module here lets the user control the feedback with a control voltage. So you don't have to put in a control voltage. This is also getting mixed by this op-amp here with a voltage that's just set by a knob on the front panel. But this is fairly flexible. So we have a setup here that creates a current for this OTA, which is basically acting as a VCA in that feedback loop, letting us control K this way. So we have the signal coming in, going into the input of this OTA. Here's that 2K, 10K kind of divide down ladder. An interesting thing about this is this does not actually divide down the voltage very much going in. That's dividing it by, let's see, it'll be 2K over 12K, so 1/6. Usually we saw a much heavier amount of attenuation in the front. So the output of the OTA is a current that's dumped down through this resistor here, and that turns it back into a voltage. And this pot here says cal on it for calibration, so this is probably not a front panel control. This is something that's set at the factory. Basically, whatever voltage you get out of this setup is being buffered by this op amp here and is being fed back to the input of this chain. Now, let's focus in a bit more detail on what's happening here. So here you can see the initial input buffer. Let's see, we're going through two 51K resistors, and those have the same resistance. So right away, whatever the signal input is getting divided by 2. This also presents a nice 102K input impedance to whatever the outside world is. By now, you're probably used to seeing these little trim pots here to deal with non-ideal effects of DC offsets in the 741 op amp. So whatever comes out of there is being input into the first stage of the filter. So this is operating as the first stage of the filter, and this bit over here is the start of the second stage of the filter. Notice that you could potentially take a signal from the outside world and plug it directly into here, into this 20K resistor, and not bother with all of this. But 20K isn't a terribly high input impedance, so it makes sense to me that they would have that input buffer in front. This 5.6K, that is part of the feedback structure around all 4 poles. Right now I want to focus on the feedback structure within a single pole itself. So here we have the OTA, and here we have a 100 ohm resistor. If you dealt with this as an ideal OTA, you would just say that this is ground. This 100 ohm here is probably to deal with non-ideal input currents. So we have this 20K resistor here, and we have 100 ohms here. So let's see, that's 100 divided by 20000. So if these cancel here, I'm using the approximation of R big plus R small equals R big. Let's see, so at this point, going into the OTA, we're dividing the voltage down by a factor of 200. So quite a lot. So we have the 3080 OTA. One interpretation of this that we looked at in a previous lecture was imagining that it's replacing the role of a resistor in an RC low-pass filter. So the current is dumped down through this cap. Here we have the C that's playing the role of the C in the RC filter, 100 picofarads. The JFET here, this is acting as a voltage buffer. This configuration with this 1K and this 10K hooked to the power rails, this is acting as what's called a source follower. So the voltage here is being buffered and provided here, and the gate of the JFET provides a really nice high impedance input. Don't worry about the 1K or the 10K. Those are just resistors that are helping this buffer do its buffery goodness. Anyway, the output here is being presented to the next stage, but it's also being fed back through this 20K resistor, and that's part of this RC where we replace the resistor with an OTA kind of structure. And so we can deal with this with a fairly simple formula because my R big going forward here and going backwards are the same. So I can take that 1/200 attenuation factor from the resistor divider, both directions, and just lump it into the gain of the OTA. Another assumption I should mention that I'm making here is that whatever else is happening down here, this 5.6K is so big compared to this 100K that when figuring out what's happening with this voltage divider, I can just ignore what's happening here and treat it as equivalent to the next stage with the 100 ohm here and so on and so forth. Now remember that the feedback around the cascade needs to be negative feedback. So let's double check that. Each individual filter stage itself is in fact an inverting filter because the input is coming in through the negative input of the OTA, and we're not doing any inverting tricks over here like putting the current through the capacitor in the feedback loop of an op amp. So, although each individual stage is inverting, I have 4 stages. So, any 2 of these stages together is not inverting because the minus signs cancel. So it's very important as we trace this through that we wind up going into the appropriate place. So since the entire structure is not inverting, the feedback loop here, if it's coming in the same direction as the input here with everything else, we need to find an inversion somewhere else. So let's double check that. So the output comes from here. This guy here isn't inverting, but it's not terribly important. What's important is that it goes into the inverting input of the OTA here. And again, we're just using this resistor to convert that output back into a voltage. The resistor is not part of the feedback loop of an op amp, so we are not getting any inversion from that. So we are getting an inversion here. It just gets simply buffered, and then it's coming back to the input here. Again, it's coming into the negative terminal, but because we have 4 of these stages and this whole thing isn't inverting, we needed to get the inversion from elsewhere, so we're getting the inversion from here. Another thing you have to be cautious about is to realize that all 4 of the OTAs here are sharing the current being provided by this PNP transistor. So whatever current is being created here, you actually have to divide that by 4 to figure out what current is going in any individual OTA, to figure out what the gain of the OTA is, and hence figure out what the cutoff frequency is. And I should say cutoff frequency of an individual stage, which is how these things are usually specified. Okay, so let's compute some numbers. Usually the cutoff of a single pole of an RC style voltage filter will have 1 over 2 pi the resistance times the capacitance. But we're using an OTA-C filter, so we'll replace 1 over R with the transconductance. And another trick we can do here is to pile the voltage division we get from that R small, R big. So I'll write R small divided by R big, and we'll pile that in with the gain of the OTA. Okay, so in this particular case, R small was 100 ohms, R big was 20 kilo ohms. So that was like 1 over 200. The gain is going to be 19.2 approximately times whatever the current going into the current control pin of one of the OTAs is. And again, we're computing the half power point for one stage. So what I would like to do is try different currents later. So I'm just going to call this a generic scaling factor B. And let's see, the capacitance is actually 100 picofarad. So I'll write 100 e to the minus 12. That's picofarad. And that will give me this constant. So let's see if I plug in 0.1 milliamp. So that's like 100 microamps. That would give me a cutoff point of 15K, which seems pretty high. If I were to put in, say, 1 milliamp, which is probably the max you would really probably want to put into an OTA in regular operation, I'll wind up with 152K, or more like 153 kilohertz. That's pretty high. Let's try 0.5. So it would be something like half that, like 76 kilohertz. So that may seem pretty high, but remember, that's just for one stage. If that's the half power cutoff and then you go through 4 stages, that's like cutting your power by 1/16. Now let's put in 1 microamp. Okay, 152 hertz. If I were to put in 10 microamps, I would be at 1.5 kilohertz. And also remember, we're driving this with a exponential voltage to current converter. So we'll have sort of a lot more resolution down on this lower end in terms of the voltages we're putting into it than we have on this upper end anyway. One thing we should be cautious about is that the currents that I was plugging in there are currents for one of the OTAs. The transistor generating the current in that circuit needs to generate actually 4 times that current because that current is being shared by the various OTAs. Ray Wilson produced several low-pass filter designs, including a 4-pole with negative feedback design, and it's very similar to the polyfusion design. He's using the special diodes inside the 13700 OTAs that try to help linearize the response of the OTA. And you see his structure here where you have a signal coming in. He's using 100K for his R big and 1K for his R small. So the attenuation factor is 1 over 100. And he's using the same R big coming in through the local feedback loop for each individual one-pole stage. So since his R bigs are the same, that means that we can take that 1 over 100, or if you wanted, you could say 1 over maybe 101 if you wanted to be pickier about it. We could take that gain factor, or I should say attenuation factor, and fold it into the gain of the OTA and use our usual formulas. Actually, like the polyfusion filter, he's using 100 picofarad caps as part of the filter, and he's not doing any tricks where the cap is in the feedback loop of an op amp. He's just using these TL084 op amps as voltage buffers instead of the JFET source follower like the polyfusion folks did. But remember, the polyfusion is a much older design. They might not have had access to JFET input op amps like we have nowadays that have high impedance inputs. If we follow the output of the 4th filter, we see that it winds up here, it gets buffered. Okay, this is a little confusing because of the way ground is written here. It makes you think that this op amp and this op amp are somehow related more than they are. If I was drawing this, I would probably put the ground here, and I would probably put a ground here and separate this to try to make that clear. Anyway, let's see, what is he doing here? He's buffering the signal coming out of here like usual, and then going to the output. He has a non-inverting op-amp configuration with 100K and 100K. So that's going to be 1 plus 100K over 100K, which gives us a 2. So for whatever reason, he likes to put a gain factor of 2 here. 1K output impedance for short circuit protection, or if somebody decides to try to take 2 outputs and short them together. Anyway, independent of that, there's the feedback loop. The polyfusion design actually had a VCA in the feedback loop, so the amount of feedback itself, that K factor, could be voltage controlled. Here, Ray is going with a simpler approach and just using a pot to determine the amount of feedback. It's being called resonance. You also hear this called emphasis and some other things. Like with the polyfusion design, the inputs to the various one-pole structures are all hitting the negative input of the OTA. There's no other inversion shenanigans going on here. So each individual stage is inverting, but the total of the 4 stages is not inverting. So we need to pick up an inversion somewhere else. Let's check that. We see as it goes through here, this op amp here is set up in an inverting configuration. So that gives us the inversion that we need. I have 100K in the feedback loop, 10K input impedance. So that's 100K over 10K. So Ray is providing a gain factor of 10 here in the feedback loop. But notice we also have this pot sitting here. So we can turn this all the way to ground, in which case we have no feedback at all at K equals 0. Or we can turn this all the way up. Now you might think that if you have that pot cranked all the way up, you would have K equals 10. But notice that we have 200K here instead of the 100K that Ray uses at the input of the OTA stages. So basically that's cutting down the gain of 10 by a factor of 2. So when we turn the pot all the way up, we basically have K equals 5. Now, I know that exceeds the K equals 4 limit of self-oscillation we had in a previous lecture, but remember that if you are into that self-oscillating region, all sorts of weird nonlinearities have kicked in, and things are getting strange anyway. The other thing I want to point out here is how similar the voltage to current exponential converter is to what's in the polyfusion design. So ignore for the moment the fact that we have a bunch of BJTs here. Let's just look at this BJT that's feeding the current control input of the last stage. If I take this BJT and this BJT, combined together, they play the same role of this PNP pair. And if I look at this op amp here with this stabilization cap, that corresponds to this op amp here with this stabilization cap. And both of those are playing the same role of holding a node at the collector of this first BJT at some sort of fixed voltage, here a virtual ground. So here you can see that the Polyfusion folks are holding this node at this virtual ground. This 15K here is just here to deal with non-ideal op-amp effects, particularly the non-ideal input currents from this op-amp that was available then. With a modern JFET input op-amp like the TL84, you could just hook this straight to ground. You don't need that kind of compensation. So we have a resistor here in the Polyfusion circuit that is helping to create a fixed reference current that's going to this negative supply voltage. That corresponds to this 1 mega ohm resistor here that's creating this reference current going to this negative supply voltage. And so everything's pretty much the same. The input structure is also similar. Just as the Polyfusion folks needed 2 op amps, where in the case of creating a current sink with an exponential voltage to current characteristic using NPN transistors, we only need 1 of these. Here we need 2. We're mixing a couple of external control voltage inputs provided via jacks with a setting set by the user via front panel knob. And we're mixing those with this op amp here. And that would give us a negative voltage, where in previous lectures we were talking about VCOs, we might take this directly to the base, or actually we would take that and drive it into the top of this trim pot here. That was okay there because the NPNs wanted a negative voltage relative to ground in this kind of configuration. But here, since we're using PNPs, this needs to be a positive voltage here, so we need to have this other op amp here to invert the voltage back. One thing different about this configuration than the Polyfusion was that in the Polyfusion, we had 1 transistor here that was providing the current that had to be shared among all the OTAs. Here, Ray is being very generous with his transistors, and each OTA gets its own transistor to provide the current. So we wouldn't have to do that division by 4 when computing the cutoff frequency of one of these stages. Now, interestingly, Ray uses the same value for his capacitors. The only difference is he uses 1K resistors for his R small and 100K resistors for his R big. So comparing that to what the Polyfusion folks did, he's basically dividing things by 100, whereas Polyfusion was dividing things by 200. So all of the formulas up here still work. You could just take each of these and multiply them by 2. So back in the day, Dave Rossum designed the SSM2040, which was basically 4 of these OTAs in a single chip, with all of them driven by the same current created by an exponential voltage to current generator that was built inside the chip itself. The chip also provided some buffers built into the chip. And one particular quirk about this chip was that in order to save pins on the package, because bigger packages are more expensive and take up more space on the board, the positive inputs to the OTAs are actually internally wired to ground. So any stage of anything you're building with this filter, each individual stage is going to be inverting. Now, you don't necessarily have to build a filter with this chip. Instead of adding a capacitor to one of these capacitor pins, you could put a resistor and build a VCA, although I don't think anybody actually does that. Basically, you, the user, are asked to provide your own capacitor, and that's great because then you could pick different capacitors and get different sort of cutoff ranges and different effects and things like that. This is a fairly flexible chip. It is not internally hardwired as a 4-pole cascade, so you could use this chip for other kinds of filters. And this is famously part of the first version of the Sequential Prophet 5 developed by Dave Smith. Notice I said first version, put a pin in that, we'll come back to that point. So if you do want to build one of these standard 4-pole with cascade structures, basically all of the stuff here is inside the chip. All of this other stuff outside of here, both the filter caps and say the 200 ohm and 10K that you see here providing the divide down that's going into the OTA, and the 10K local feedback caps here to create those one-pole structures. Again, we're conveniently picking the 10K and the 100K to be the same so we can use some nice formulas and fold that effect into the gain of the OTA. Well, if we're going to have some feedback, again, because each of these stages is individually inverting, the four of them together are going to be non-inverting. Remember, the positive inputs of the OTA are actually internally hooked to ground. So let's check the feedback path. So here the SSM2040 datasheet presents us with a scheme that uses an SSM2020 in order to provide variable feedback gain. So the SSM2020 is no longer in production. It's a little weird, and the schematic here is actually kind of confusing. All of these dots here indicate pins on the 2020, and as far as I can tell from the datasheet, basically the 2020 is an OTA with some voltage to current creation circuitry built into it. The details of this aren't terribly important. The main thing is that there's something here that lets you control the amount of feedback gain. Now, remember that even though each individual stage is inverting, the four stages together have all of those minus signs cancel and are non-inverting. So we need to pick up an inversion somewhere else in the feedback loop, and we can pick it up here. So we have this op-amp here set up in an inverting configuration, and then the output of it is fed to the positive terminal of this OTA that's part of this SSM2020 chip. So this is where we get the needed inversion. Notice there's one other little weird thing about this. There's a gain of 10 at the output here that you get through this op-amp, since I have a feedback resistance of 100K and an input resistance for this inverting setup of 10K. So from that gain of 10, you might expect there's a attenuation by a factor of 10 elsewhere, and you actually get that here. There's no harm in analyzing the circuit in imagining that you don't have one of these zeros here, so that 10K here matches all the rest of the 10Ks we see everyone else. And then you could think of that additional factor as 10 as just affecting the signal right at the input. So unfortunately, the SSM2040 apparently had some reliability issues, or at least reliability issues the way it was used in the Prophet 5. So later revisions, the revisions 2 and 3, went to the CEM3320 integrated circuit, the 3320. Now, this looks like an unholy mess just because the schematic is written in terms of the native pinout of the 3320. If you take this schematic and you unravel it, then you get something that makes sense. It's very much like the 2040 chip where you have a bunch of OTAs, and in particular, you've got 4 of them, like on the 2040, and then you have a buffer at the output of each of those OTAs, and then you have a place where you can provide your own capacitors to ground for the filter capacitors. Let's see, where's the other one? Let's see, here's a capacitor, where are, here you are. So they're all spread out, but the circuit is basically this circuit here. It's just all tangled up weird. All of the input currents to all the OTAs are created by this exponential voltage to current converter. And a cool trick that the 3320 has that the original 2040 doesn't have, it actually has a whole other fifth gain control element, specifically to handle changing the amount of gain in the feedback path to change that K factor. So like the SSM2040, this is a fairly flexible chip. It's wired here like a 4-pole with feedback filter, but you could create other designs with this. The 3328, on the other hand, is very much hardwired to be a 4-pole with feedback filter. So here you can see the 4 gain control elements in a row, and these are all driven by the same exponential converter. But this one, if you untangle it, you'll see is internally wired to act as a 4-pole cascade, so it doesn't have the level of flexibility of what we've seen previously. One of the most popular devices it was used in was the Ensoniq Mirage, one of the first reasonably affordable samplers on the market. And you can find it in some obscure analog synths like the Krumar Bit 01. And one thing I want to point out here about the Ensoniq Mirage is the Mirage was a sampler, but a lot of these samplers from the early 80s had individual signal paths for each voice with fun stuff like analog filters in them that you could use to sort of blur the lines between sampler and synthesizer. Now, the SSM2040 itself was long out of production, but it was muchly loved. So people have tried to recreate it using discrete transistors. And this is one example of that from Renee Schmitz's webpage. And there's also been some fine work done on this by Jürgen Heibel and Ryan Williams. Down here, you can see the current control generation. And like in Ray Wilson's design, each individual stage here gets its own BJT, unlike in the Polyfusion where all of the OTAs had to share the current created by one transistor. And we have our feedback path here. And in this example, a potentiometer is controlling the amount of feedback. Here we have the individual stages. We have 4 filter stages. So now I would like to focus on just one of the stages. Don't let all of these plus 5 volts throw you. These are sort of actually acting as a local ground, kind of the way in guitar pedals that usually run off of a single-sided 9-volt supply will internally have 4.5 volts, kind of acting as the 0 signal reference inside the pedal. Anyway, if you think about it that way, you can imagine the bases of these transistors as forming the positive inputs of the OTAs in the original SSM2040, in which case you would think about the bases here as forming the negative inputs. What do we have? We have the input coming in through here into the negative input of this primitive OTA. And we also have the output being fed back through this 10K resistor here to the negative input of this OTA, providing the local negative feedback needed to form that one-pole filter. All of this stuff here is acting as a primitive OTA, like we saw in the Buchla 259 circuit, where we have a current mirror up here, and we have a differential pair down here that forms the input. We need current sinks instead of current sources the way we would for something like a 3080 or a 13700. This is forming the voltage buffer. This set of 2 transistors is called a Darlington configuration, and basically these 2 BJTs are acting as a super duper extra awesome BJT. So if you just think about that as a single BJT, when I'm combining it with this 10K resistor down to the negative voltage rail, this is acting as an emitter follower. It's acting as a voltage buffer. So the voltage that's formed here from the current output of this primitive OTA going down through this 1 nanofarad cap, the voltage that's produced by that is being buffered by this structure and reproduced here. And then that buffered voltage is what is being locally fed back here through that 10K resistor. Now, there's some issues associated with using BJTs in this buffer configuration. If we had just one BJT, you do get a diode drop somewhere around 0.6 to 0.7 volts from the input to the output. Here, because we have 2 transistors, we have a diode drop of around 1.4-ish volts. And that's something you don't get with JFET source follower voltage buffers. So Ryan Williams has an excellent article analyzing this core and doing all sorts of circuit simulations that I would suggest you check out. The last example here is from a patent by Arp, and this one's a little bit dangerous. There's actually an error in here. Now, the basic core structure of each of these one-pole filters is pretty much the same as what we've seen before. We have an operational transconductance amplifier. It has a gain controlled by this current input. Here, instead of the positive terminal being grounded like most of the designs we've seen, the negative terminal is grounded and the signal is coming into the positive input here. The main difference is that instead of running the current output of the OTAs through caps to ground and then buffering that, here the capacitor is in the feedback loop of an op-amp. Now, don't be thrown by the fact that you only see one input here. This is really indicating the negative input, and you can imagine that there's a positive input that's grounded. Well, even though we're coming into the positive terminal here, because we have the capacitor in the feedback loop, this entire structure here forms an inverting filter like we've seen previously. And like we've seen previously, because we have 4 of them in a row, all of those minus signs cancel, and the total cascade is non-inverting. So here's where the error is. I have the output coming out here, and it's coming back to the input along with everything else, but it's coming back to this main input without any inversion having happened in the meantime. So what you really want is the resonance path, this negative feedback path, to come back to this negative input terminal somehow. So everything we've looked at so far have been low-pass filters. There are some 4-pole high-pass filters, but they're fairly rare. Polyfusion has one, and I think they probably have one largely because Moog also had a 4-pole high-pass filter. Now, Moog's 4-pole high-pass filter doesn't look anything like the OTA-based designs we're looking at here. The high-pass version of the 4-pole low-pass filter Moog made also doesn't really look anything like the low-pass version of that filter. It's very much its own thing. Anyway, if you look at the circuit, it's almost identical to the low-pass filter. All of the stuff down here, all of the circuitry to handle the voltage-controlled amplifier in the resonance feedback path, and all of the stuff that's generating the control currents for the OTAs, this is all the same. The only real difference you'll see is that instead of the input after being buffered going to the negative terminal here, it goes into the capacitor. Remember, in the low-pass version of this, we had the cap going to ground, but here it takes the input, and then here we have the usual feedback path. So I haven't actually looked at the PCBs for this, but I could imagine that Polyfusion could have made one PCB with all of the basic structure in here, and then just change some places where they either populate or not certain footprints for certain parts, and build the low-pass and the high-pass version of this from the same board. I imagine you could probably also put in some switches and switch the various individual stages from high pass to low pass. You could even have maybe a couple high pass followed by a couple of low pass and then see what feedback around that does. I think actually the Elka Synthex can play those sorts of tricks. Anyway, very similar to the low pass filter.